Yesterday we looked at the procedure for designing the signal. It has 3 steps. Okay, the first step is to have a phase diagram, develop the phase diagram. Okay, or the phasing plan. Phasing plan. The plan should be effective and safe. Effective means try to merge, combine movements as much as possible. But at the same time, safety. Okay, so those movements which are conflicting cannot be merged. Okay, and I gave you some guidelines because there is no fixed phasing plan. Okay, it cannot be fixed. So there are some guidelines, and then there are 2 types of figures through which you can show the phasing. We have the phase diagram and we have the ring diagram. Okay, today we will move to the second step of the design process was calculating signal timing, which we will try to cover some of it today. And the last step is to check for pedestrians. Okay, phasing, then timing, then pedestrians. So as I said, we will start with the timing, the calculation of the timing. The first thing we will calculate is yellow and all red. Okay, yellow is also called as change and all red is called as clearance. So you see the equation of yellow over there and all red equations are over here. The yellow on the left hand side. So we have T here, which means the reaction time. T means the reaction time. Okay. Now where did we use the reaction time? Highway, where? What? Calculating what? Side distance. Side distance. It's the same value. It's the same value. The reaction time used for stopping side distance or any side distance. Then we have S85, which means the 85th percentile speed. Now in which topic we found the 85th percentile speed? So what was the topic? Spot speed. Okay. The only topic we did for speed. Spot speed. Okay. So to find out 85th percentile speed, I need to have the frequency distribution table and you need to plot the cumulative frequency graph, and from there you find out the 85th percentile speed. But that means you must have the data. Okay. If you don't have the data, okay, somebody else did the study. He gave you the average value and he doesn't trust you. Okay, so you don't have the data. So what to do in that case? So we have this shortcut over here, that 85th percentile speed is the average plus 5. Okay, average plus 5 will give you 85th percentile speed. Then we have the A value, which is a deceleration rate. We have some standard values given by AASHTO. Then we have 64.4, it was basically 2 into gravity. So they put the value of gravity, 64.4, and capital G is gradient. Okay, capital G is gradient. Moving on, now we have the all red or the clearance interval. For clearance interval, you have to look how many pedestrians are crossing the road. What pedestrian movement you have. If you don't have any pedestrian movement, you will use the first equation. Okay, so the first equation is used for calculating all red if there are no pedestrians available. Okay, so what do we have? W. W is the distance from the stop line of one side to the stop line on the other side. Okay, so stop line one side to the other side. W. L, length of the vehicle, standard length of the vehicle. Car. So the standard length of a car is 18 to 20 feet. Okay, and then we have S15, which means the 15th percentile speed. And again you need the frequency distribution table and curve and so on. And if you don't have this, then we have this thing. 15 is average minus 5. 85th is average plus 5, 15th is average minus 5. Okay? But the ideal thing is you should have the curve. So this is the case where you don't have any pedestrians. The next case is when you have high number of pedestrians. Okay, the pedestrians are there and they are in very high number. Okay, so what's the difference between this equation, the first one? Huh? This one and this one, this one and this one. What's the difference? What's the difference in the equation? W and P, right? We are using W here and we are using P here. What is P now? P is the distance from the stop line to the crosswalk on the other side. Okay? P was from stop line to the other side, the stop line itself. And W. W was from stop line to stop line. P is from stop line to crosswalk. Okay? L is the same, S15 is the same. Okay. Now let's say you have a case in between them. Okay, the first case was no pedestrians. Second case was very high number of pedestrians. Okay, if you have some pedestrians, few pedestrians, so you cannot neglect them, but they are not very high. Okay, they are not very much. So then we come to this expression. Okay, here there is nothing new here. No new value here, right? All values we know. The only thing is you have to calculate two ratios, both of them, and they are not multiplied. There is a comma between them. This is a comma. Okay? So you will calculate the first ratio and the second ratio, and then you will take maximum. Clear? So yellow, one equation, all red depending upon pedestrian volume. Clear? This is a figure which is showing P and W, I already explained. Stop line to stop line, W. Stop line to crosswalk, P. Okay. This is an example. We have to find out the change and clearance, meaning yellow and all red, for this data. Okay. Okay. So I start with calculating yellow. Okay. So we have average speed, gradient, distance from stop line to the other lane. Which value is this? Which value is this? We don't need it. Okay, we'll talk about it later on. Okay, to calculate yellow interval, do you need anything to calculate the yellow interval? Everything is given or not? Yes. So we just put all the values?
The axis, time and the gradient.
S85, right? We need S85, and what they have given? Average. Okay. So how much is S85 if we have the average? So S85 equals 35 plus 5. Okay, yellow. Yes. What else?
You said it's the time required to stop.
No, reaction.
We check the grade as positive and negative to see the highest value.
Negative.
When we take negative, even if it is positive, even if they give us positive.
No, if positive, we take positive. reaction time is 1 second. How can you get 0 point something? You are adding it, right? So 1 plus all this gives you 0 point.
3.93. 3.93.
3.9. Already. Gradient is 0.025, huh? 0.025. No. How much? 3.93? 4.2? Hmm? Okay, no problem. It's a small difference. 0.0 something here and there. No problem. Okay, clear? Any question in this? Okay. For the all red, there is some pedestrian present. Okay, so I have the third case. This one. Third case. Okay, so AR will be okay. So what is the first thing you will do? Calculate what? S15. But we are in S40, right? We are in S40. 41 is 10. Okay. You didn't get it. So 35 minus 5. We are in S40, right? I'm sure some student will ask in the exam, how can you give us S85 when you are building S41? Inshallah. What? This. What same equation? Which same equation? This. Now we are calculating all red. We are calculating now all red. Yeah, 20. Vehicle length, right? L is vehicle length given. Even if it is not given, 18 to 20 feet, standard. How much is? How much are these ratios? .5. Okay, we have to take the maximum one. That means I will take this one. I take what? Any questions? Clear? Is this clear? Okay. Everybody, clear? The next thing is very, very difficult. That's why I'm asking again and again. This is clear? Okay. Next thing is lost time. Every phase has two lost times. Okay, startup lost time and clearance lost time. Clearance is when? When is the clearance? All red. And when is the startup? All green. Okay, so it's the start of green basically. Okay, the start of green, the first 3-4 vehicles are taking more time. That more time is the startup lost time. Okay, I already explained, if you want to know the value of startup lost time, you can do a headway study at the intersection. Okay, you will know the exact value. Okay, but if you are as lazy as you are, then we have a recommended value, which is 2 seconds. Okay, so 2 seconds is a recommended value, which is from AASHTO. You can take it if you don't have any local data. Clear? So startup lost time, we know we can take a recommended value, or we can observe. Okay. Now for the clearance lost time, why do we call all red as the lost time? Because nobody is entering, right? Everybody has red, nobody is entering. Okay. Now this is a very, very difficult part. Pay attention. There are some people in the world, somewhere. They are somewhere. Okay, they see the signal yellow. You listen. They see the signal yellow. Okay, and they think it will turn red. Okay, so what do? They prepare to stop. Okay, and what actually happens? Yes, then they feel stupid because the signal didn't turn red. So but they already decided I will not cross. So now they have to stop. Okay, so this happens when people are somewhat distance away from the signal and they see the signal is yellow. Okay, so those people, based upon the assumption that it will shortly turn red, they already prepared to stop and they will stop no matter what the signal is showing at that time. Okay, that time in which vehicles usually cross always is the first 2 seconds of yellow. Okay, again according to them, first 2 seconds of yellow. In the first 2 seconds of yellow, people usually cross. Okay, people who come after that, there are more chances they will stop. When they will stop, everybody stop, right? Nobody is entering, everybody is stop. So even if the signal is yellow after the first 2 seconds, but nobody is entering, so that is lost time, right? Even if the signal is yellow and nobody is entering, it is lost time. So any time, according to them, after the first 2 seconds of yellow is lost time, clearance lost time. Got it? Okay, understood? They see us, they will put a minus here because we are looking even 2 seconds after the yellow, right? You agree? Okay, so if I want to calculate the clearance loss time, okay, so I will take yellow and all red. Okay, so we calculate yellow and all red, right? Yellow and all red. I'll add them together. Okay, so they will become the yellow and all red total. From this total, how many seconds are used by the driver? 2 seconds. The remaining is lost time. Okay, so total 4.2 plus 1.5 total time available. After that, 2 seconds used, the remaining lost time, clearance lost time. Okay, now if I want to find out the total lost time, I'll add the startup lost time with it. Okay, so this is the clearance lost time. If you want total, you will have startup lost time to be added. You can add the value, your local value. If you don't have it, then you will use a standard value, which is 2 seconds. So this will give you total lost time. Got it? Okay. Yes, it will become same. Okay, but the values can change, right? These are recommended values. They can change. Okay, so you must know what is happening. Okay, you get it? What is happening? Okay. Any questions? Clear? Okay. Next thing is to find out the critical lane volumes. What is the critical lane? The lane which needs what? More time? Why not more volume? Why did you say more time, not more volume? Huh? Always? Always? No? Why? Give me an example.
Just to the left of the straight.
Ma'am?
Because the straight it is just straight.
It is not straight, yeah. So no, more volume is always not more time, right? Agreed? We can have heavy vehicles and they may take more time. We can have a turning movement, it may take more time even if it is low. It can happen, right? Okay, so for example, now remember we already have the phasing, we've covered the phasing plan. So now we are assuming that phasing is already done. I know which movements and which lanes are open when. Okay, which green is for which lanes and so on. Okay, now I have to pick for each phase a critical lane. A critical lane. Okay, so for example, I have 3 lanes. I have to pick one of them as critical. I said the one which needs more time, right? But I only have what? Volume. Okay, so how can I decide on the basis of volume which needs more time? Or which one is more critical? I cannot. I have, for example, 3 lanes, one for, or let us start with the one which you already know. 3 lanes, okay, all having different number of heavy vehicles. So how do I know which one needs more time? I only have a number, right? Got it? So in order to compare between them, they must be in same units. Okay? If I tell you this one has 500 vehicles, this one has 400 vehicles, this one has 600 vehicles, but in those 600 there are some heavy vehicles. Those heavy vehicles can increase the time, right? So based upon number I cannot decide. Maybe the 500 will take more time because of heavy vehicles, right? To select a lane, I need all these 3 values to be in the same units. Okay? Not these many cars and these many heavy vehicles. Okay? So, converting volume to passenger cars, what do we need? Factor of heavy vehicle. Okay? So, this we already know. If you have 3, 4 lanes, whatever number of lanes, okay, you take the volume for each one of them, divide by factor of heavy vehicles, all of them are now passenger cars. So one problem solved. All of them are now in the same units, all of them are passenger cars. So now I can compare. Okay, after dividing by factor of heavy vehicles, they are in the same units. So this one has 400 passenger cars, this one has 300 passenger cars, this one has 500 passenger cars. So obviously now my decision is very simple. Got it? Clear? Okay? Clear or not? Now, what if I have 3 lanes and one of them is turning, or 2 of them are turning? Again, I cannot compare. I cannot compare straight with turning, because maybe the turning has less volume, may still need more time. So I have to make them on the same basis, on the same scale, right? So like I have factor for heavy vehicles, I have factor for turning as well. Okay? These tables provide equivalency factor for turning movements. So you have a turning volume, you want to convert it to straight, you multiply with one of these factors. So the table on the left hand side is for left hand turning, and the table on the right hand side is for right hand turning movement. Okay? If you want to convert the left hand turning movement into a straight movement, you will multiply with one of these factors depending upon what? What do I need? I need how many lanes are on the opposite side. Okay, so if I am turning from east, then I need how many lanes are from the west side. Okay, and the volume, same lanes. Volumes, again, the opposite lanes. Got it? Okay. Now, why do I need this? Why do I need the opposite volume? Because you don't allow it, right? Same phase. The left turning and the opposite volume should not be allowed, right? Some of you are thinking, what is happening? You are turning left and somebody is coming from the other side. Would you allow it? No. Okay? It's not allowed. Okay? So these factors are to be used when the left turning is allowed because of some reason. We don't have it, obviously. We don't have it. Don't try to imagine. Okay? Don't try to imagine. It's not there. Okay, clear? It will be your last imagination. So we don't have it. Okay? Because of some reason in some country, if they allow the left turn, like left turn is allowed, like we have the right turning allowed. If the left turning is allowed in the same manner, then you can find the table, find the factor from this table. For our case, when the left turning is restricted, we will use this value, 1.05. Clear? Okay? So if the left turning is allowed, then you can pick a value from the table. If it is restricted, just 1.05. Clear? Now right turning, look at the table for right turning. When you come to the right turning, then we don't have any opposing movement, right? Nobody is coming from the opposite side to cross you. Okay? But what do we have? We have pedestrians crossing. Okay? So then I need the pedestrian crossing volume to find out the factor. No pedestrian crossing, 1.18. Above 0 up to 50, 1.21, and so on. Clear? Clear? Any questions?
Do it interpolate.
Huh?
Do it interpolate.
Yes, you can. No, we don't have. Actually, this is the range, like more than 0 up to 50. Can take this value. Run it interpolate. It's a range.
More than 800.
Huh?
What's it? It's more than 800.
Same fact, 2.1. Last value. Okay, clear? Now, so you have some left turning volume. You have one lane which has left turning volume. You take that volume, pick a factor from here, multiply with that. Okay, you have a lane which is for right turning, or you have a lane which has right turning vehicles. Take those vehicles and multiply with the factor for right turning. Okay, so they will become what? They will become equal to straight vehicles. The turning vehicles become equal to straight vehicles. The term which is used for straight movement in the book or in signal design process is through. So through means straight. Through means what? Straight. Okay. So turning vehicles will become equal to through vehicles. Got it? Okay. So now once you converted the vehicles to passenger cars and through vehicles, remember these are two conversions. You need both of them. One of them you already covered. Okay. Once you convert it, so everything is now passenger cars through. Now you can compare, no problem. Compare this lane with this lane. If it is turning, if it has more heavy vehicles, doesn't matter. You already made the equivalents. Clear? So now you want to compare between the lanes. You want to add all of them. Now you can add. Okay. You cannot add left turning with right turning, right? They are two different things. Okay. They are like apples and bananas. Okay. So you cannot add them. You can eat them. You can add them. Okay. And if you want to calculate average volume per lane, again, add all of them, divide by number of lanes. It's fine now. Okay. So without the conversion, you cannot use these volumes together for any case. For comparison, for summation, for average, you cannot use them because these are different things now. After the equivalency, then they are now same. You can add them and do whatever you want. Clear? Clear? Okay. Now, how did we get the factors? Okay, just a small example from a field study. We have a signalized intersection. It has two lanes. One of the lane is only for through. Through means straight. And the other lane is for two movements. From the other lane, you can go through or left. Okay, so how many lanes we have? Two. One of them for through, the other one for through and left. When the signal became green, they observed both lanes for the same amount of time. Okay, let's say the time was x. Okay, so both lanes were observed for x number of seconds. Okay, in x seconds, from one lane, 20 vehicles passed. Okay, in the same time, from the other lane, I had 10 vehicles going straight and 5 taking a left turn. The time is same. So 20 from one lane in x seconds and 10 straight and 5 left from the other lane in x seconds. Something is missing here. What? This equation which I wrote here, what is missing? Conversion factor. Where should I put it? Where should I put it? With the 5, because you cannot add 10 and 5 without the conversion, right? This is what I said. Until you convert 5, you cannot add 10 plus 5. 5 is something different now. Okay? So with 5, there should be ELT, the left turning equivalency factor. Okay, can you calculate ELT? Nobody is saying yes. No, we are calculating it.
5.25.
Whatever. Give me the value.
5.25.
Huh?
5.25.
Can somebody give me the value of ELT here? What? How much?
For them to be equal,
Huh?
for them to be equal,
Yes.
2.
2. How much is it? 2? You will not say it. This is an example how to calculate the factor. We are not using the factor. Okay? We are calculating the factor. This is what you can do to calculate the factor. Okay? Observe different lanes for same time, equate them, and you can calculate the factor. Clear? Yes.
Why you assume that both of them are critical lengths?
At what?
Are critical lengths?
I didn't assume. I just observed them.
Why you assume that they equal to equal?
To calculate the factor.
Yeah, the factor from the table.
I don't want to use it. That's for US, right?
Why? Why are
What
they
why?
equal?
Hmm?
Why are they equal?
Because it happened at the same time. I had one queue here, one queue here, and both of queues were moving. Okay, so this queue in X number of seconds passed 20 vehicles. This queue in X number of seconds passed 10 and 5. Okay, so now I'm using this data to calculate the ELT. Okay, whether we use it or not, that's a different thing. Okay.
Then put that value on the critical volume.
Right now, we are just calculating the factor. In this example, we are just looking at how to calculate the factor. That's it. Okay, those factors came from somewhere, right? Huh? Like I gave you the value, recommended value for startup loss time, but I showed you the procedure how to get it. Okay, so this is the procedure how to get it. Okay, in the end, obviously, we have some values which others have taken. So we will take those values. Clear? Clear or not? Anybody has any questions? No? Okay. This is something similar to what we have done even in the last chapter for heavy vehicles. Okay, we have a volume 1350. Out of this, 8% are left turnings. Out of 1350, 8% are left turnings, and the factor for left turning in this example is 2.7. Okay, for this example it is 2.7. They are asking for total equivalent volume. Total equivalent volume. Meaning what? In this 1350, they did what? Through plus left. Add them together, which is not accurate. Okay. So, to make it accurate or to make it equivalent, what should I do? Convert the or multiply the left turning with the factor. Okay, so first of all, I should know how much is the left turning volume. How much is it? 1350. How much is this? 108. For these 108 vehicles, the equivalency factor is 2.7, right? 2.7. So 108 into 2.7. How much? Huh? Okay. So this is the equivalent of left turning. Okay. I want total through. Total through. Okay. So the equivalent is already there. Yes.
1350 minus 108 plus 290.
Yes. So 1350, which was a total, minus 108, which is for left turning, because left turning is already converted. So now I will add the converted value. So this gives me how much?
1534.
153. Okay, so this is the accurate volume because now everything is through. Okay, clear? Any questions? Yeah, we will do it. Yes. Okay. Step by step. Okay, like I said, we cannot do everything like first convert passenger cars, then do this, then cycle length. So it will take a lot of time. Okay, so we do one step at a time. Okay, other step now you know it, like S85, right? S85 we did in spot speed. I showed you how to do it. If I keep on doing it out for every example, it will take a lot of time. Okay, which is what you want, I know, but we will not do it. Okay. Now for the remaining timings we will calculate from this example. Okay, so pay attention. Now we have what? We already have the phase plan, which you can see over here. They developed a phasing plan and they are showing it here. So I know which movement is going first, which movement will go with this, and which movement will go after it. This is the phasing plan. Which movements are going together and which movements are going separately, and which one will go after what. Okay, this is a phasing plan. What do we call this diagram? Ring diagram. Okay, why? Because we have different directions in different boxes, so we call it a ring diagram. Okay, in phase diagram, all directions, if they are in the same phase, are in one box. Okay, clear? So this is a ring diagram. Now I have four phases. A1, A2, A3 and B. Okay, don't get confused because of the name. You can give it any name. Okay, give it any name. Osama, Ahmad, whatever. Okay, you can have a phase for each one of them, no problem. Okay, but there are four phases. Why four phases? Whenever a movement changes, phase changes. A movement changes, phase changes. You see A1, this movement finishes, A1 finished. A2, this movement finished, A2 finished. A3, both movements are finished, obviously, so phase is finished. Okay, any one movement changes, phase is finished. Clear? That's how I have four phases. For each phase, they already did the conversion. All vehicles are into passenger cars and all turnings are through. So now I can compare directly, no problem. Okay, so maybe this one had two lanes, they already compared and they give me the critical one. They converted and compared, this is the critical one. So for this movement, this is the critical one. For this movement, this is the critical one. Okay, so for each movement, the critical one is given. Okay, for each movement, the critical volume is given. And all of them are converted, passenger cars through passenger cars. Clear? Clear? Now, what I have to do is find out the total critical volume. Total. Okay? So, phase B is very easy. I have two movements here. Both are simultaneous. Okay? For this one, it's 280. And for this one, it is 300. Which one we will pick for critical? 300. So, for phase B, I will design for 300. From phase B, I will pick 300. If you look at phase A1, okay, now A1 also has two movements, right? It has overlapping like the other one. So 150 and 250. Can I pick 250 for design of phase A1? No, because it is continuing in the other phase, right? All 250 is not in A1. You will overestimate. Same problem with A2. 600 here, 250 here, 550 here. 550 is not here. 600 and 250. But if you pick 600, 600 is not in A2 only. It's also in A3. Okay. So now we have movements which are continuing from one phase to the other. So what do we do in that case? You have to take the entire sequence now, entire series. Okay. So this is one series and this is another series on the right hand side and the left hand side. Why I am calling them different series? Because these are conflicting movements. Look, the first one, 150 left turning, right? And the next one, 600 straight from the other side. They are conflicting, right? So this is one sequence because they cannot be parallel. These two cannot be parallel, so they are in one sequence. Same thing here on the right hand side. 250 turning, 550 opposite through. So again they cannot be parallel. So this is another sequence. Okay. So for critical volume, I will take the entire sequence now. Okay. So if you take this sequence on left hand side, 150 plus 600. How much? 750. Okay. If you take the sequence on the right hand side, 250 plus 550. How much? 800. Which one is critical? 800. Okay, got it? So if you have overlapping, the first thing I already mentioned, you have to convert all the volumes, you can compare. Okay? And once you convert it, now you can see which one is higher. If you have a situation like this, where movements are going from one phase to the other, then you will look at the entire sequence of phases and pick the higher one from the entire sequence. For each phase, not possible. Clear? Okay? So 800 from here and 300 from here, total 1100, right? So this is my total VC. Total VC is 1100. Okay. Now we can calculate the cycle length. This is the equation of cycle length. We have used it earlier as well. Okay. So here I will just add VC. Okay. So loss time per phase is given, peak hour factor is given, V by C ratio is given, saturation headway is given, VC we calculated. How many phases we have?
4.
Phases. How many phases?
6. 4. Each phase. Each movement.
No, but movements are overlapping, right? Not for each movement. What? Two overlapping movements in same phase. Like B, same phase. 4 phases. Sure. Any confusion you ask me? Because you saw the 3. Very good. So next time I will write 6 with B. You will see the 6 and you will tell me 6. Right? 4 phases. So how much is the cycle length? N is 4. What? Yes, tell me. 63 point what? Yes, correct. Tell me. Okay, and as I mentioned earlier as well, we rounded up to the nearest, not the nearest, the next 5 or 10 seconds. Okay, so you can round it off to 65 or 70, no problem. Okay, 65 or 70, no problem. Clear? Okay, any questions? Okay, now the last thing we will do is calculate total effective green time. What is total effective green time? Cycle length minus total lost time. Cycle length minus total lost time. How much is the lost time? Tell me.
3 seconds.
3 seconds per phase. So total is?
12.
Yes. Okay, cycle length 65 minus 3 seconds for each phase, and we have 4 phases. So how much is this? Clear up till now? Okay, we will continue with this same example with the same values. Okay, for the remaining calculation. Okay, so when you come on Thursday, bring these values. Clear? Any questions? Okay, thank you.